Good evening. This is Professor David J. De Los Reyes. Okay, it's December, no, January 3, 2023. My topic for tonight will be a new topic. It is still on second order differential equation. I will give you an application problem of a second order differential equation. Another variation problem on second order differential equation. Okay, I will try to read the problem. Okay. I will try to read the problem. The force exerted by a spring is proportional to the amount that the spring is stretched, and the value is 200 pounds when the spring is stretched 1 foot. Okay. A 64.4 pound weight is suspended by the spring as shown, and is released from rest 0.4 feet below the equilibrium position. This is the equilibrium position. Okay. The weight was pulled down at a distance of 0.4 feet from the equilibrium position. Okay. The question is, find the equation of the motion, the amplitude. Why amplitude? Because whether we like it or not, if you try to, what you call this, pull down the weight, then release it, it will try to oscillate, right? The amplitude is actually how high and how low is the motion. That's the meaning of amplitude. Find the equation of the motion, the amplitude, the period. Period is actually for one cycle, one complete revolution, what will be the total elapsed time? Meaning as it covers up the upward and downward motion, that's one cycle. And what will be the so-called period, the total period. And the frequency. Frequency is actually, it oscillates, so there will be a frequency. So as a summary, it will be something like this. There's a frequency for the motion. As it goes up and down, there's a frequency. And what will be the frequency? Okay, I will try to repeat the problem. We are given a spring, and suspended from the spring is a weight W. The total weight is actually 64.4 pounds. Or the mass is actually weight over gravitational acceleration, that is 64.4 over 32.2, it is 2 slugs. It was given to the problem that the mass is 2 slugs. Slugs is actually the unit under the so-called English system. The spring constant is given by the value when the force on the spring is 200 pounds. You could stretch the spring 1 foot. We needed this one in the calculation of the motion, okay? Because the value 1 foot and 200 pounds, that's how strong the so-called spring is. Like the vibration, no, it's not vibration spring. The suspension spring of cars, okay? As you try to move around, okay, actually the car is actually moving up and down due to the so-called suspension spring. So it is similar to this, okay? The condition, the problem is asking, find the equation of the motion of this. Because supposed to be, if you try to stretch the weight going down, then release it, whether we like it or not. The weight should try to move up, move down, move up, move down, move up, move down, till come a time that it will go to rest, meaning it will go to the equilibrium position. So actually, the graph of the summary is something like this. It is an oscillatory motion. It goes up, down, up, down, up, down. It is an oscillation. It got an oscillation. So amplitude is involved. Amplitude meaning how high or how high is it? Going down, going up. That's the amplitude. And for one motion up and going down, what will be the total time? Okay, let's proceed with the solution. To bring out the solution of this is now differential equation subject matter DE44. The title is second order differential equation application. This is with regards to oscillatory motion. The last example I've given you is actually the projectile, the one that goes up like a missile, right? I will check my camera. So right now, what is being given is actually an oscillatory motion. Oscillatory motion, it falls under second order differential equation. Okay, let's try to bring out the figure. We are given a spring. Below the spring is actually an attached weight. The total weight is 64.4 pounds. The given condition in the problem is, the given condition of the spring, how strong the spring is. If you stretch the spring 1 foot, the applied force is 200 pounds. So you will know, if you stretch it 1 foot, okay, it could carry 200 pounds. The problem is asking for y as a function of time, meaning the equation of the motion, okay? It should be y as a function of time. It should be with respect to the vertical. Okay? The amplitude is actually, it goes up, it goes down. Okay? But what will be the value of that value? Distance. The term for that is actually amplitude. Period is actually the total motion going up, going down. What will be the total elapsed time? That's period. And frequency. Frequency is just the reciprocal of time. So if we know the period, we could compute for the frequency. It oscillates like this. So for one cycle, if it is 10 seconds, what will be the frequency? So if you know the so-called period, total time, you could compute for the frequency. So as soon as we could compute for y as a function of time, we could compute for the amplitude, we could compute for the period, and we could compute for the frequency. Okay, let's try to bring out the solution, please, by using differential equation. Under one laws of, what do you call this, one laws under dynamics, that is, force is equal to mass times acceleration on any moving object, okay? The net force acting on that body should be equal to its mass times acceleration, okay? For the given spring problem with the given attached weight, okay, I will place this capital letter F here to be small letter f. This small letter f is the so-called frictional force exerted by the spring on the weight. Because whether we like it or not, if the weight is attached to the spring, okay, there should be a force that will contradict that motion because the spring is very strong, right? So we will place it negative. Why negative? It contradicts the motion, right? And this should be equal to mass times acceleration, that is force acting on any moving body, okay? We place the negative sign because it is opposite the direction of motion. So if the motion is downward, the contradicting force due to the spring is actually F, and this should have a negative value. That's why this is negative. Okay? Okay, let's stop for this time for a moment. Let's compute for the value of F. The frictional force on the spring is actually given by the relation. Frictional force is directly proportional to Y. The force exerted on the spring is directly proportional, or how wide is the, what you call this, stretch, okay? that is F is directly proportional to Y, or in terms of equation, frictional force due on the spring is equal to certain constant K times Y. Y is the stretch area, length, right? And for the given problem, if we apply a force of 200 pounds, you could stretch the spring by total length of 1 foot. So if we are given F here and we are given Y, actually we could compute for K. That's the property of the spring we are using, right? So substituting the 200 in 1 foot, 200 should be equal to K times 1. K now will be 200 over 1. K is actually 200. Meaning the spring constant is 200 pounds per foot. We need this one to compute for the equation of the motion. Then we'll go back here. Since K is equal to 200, okay, 200 now times Y, okay, times Y. And this should be equal to mass times acceleration. Mass times acceleration. Mass is actually weight over gravitational acceleration. Under the English system, the gravitational acceleration is 32.2. So this will become 64.4 over 32.2, and this is equal to 2. And this is actually given. I just presented the solution, right? Times acceleration. The acceleration of the weight as it moves up and down. And in terms of the variable distance y, this should be d square y over dt square. Simplifying this one, 200 over 2 will be 100. So this will be gone. This will become 100. Sorry for that one. Rearranging the equation, d square y over dt square, we will place this one on the right, then we rearrange plus 1 on the y equal to 0. The variable distance is y with respect to time, this is y. So we are now given a second order differential equation. That's why I told you the application problem is under second order differential equation. So this is SODE, second order differential equation. And as we have presented on the previous discussions, the solution is actually y equal to k e raised to mt, dy dt, take the derivative of this, it will be km e raised to mt. D square y over dt square, take again the derivative of the first derivative, what will come out will be km square e raised to mt. We take this value y here and the second derivative. Unluckily, we don't have the dy dt here, right? Okay, what will come out? So substituting, this should be km square e raised to mt plus 100 times k e raised to mt, and this should be equal to 0. The common factor is k e raised to mt, so actually we could divide all the terms by this, so this will be gone. And this should be gone. So what will come out after the division of that factor? It will be m square plus 100, and this should be equal to 0. We term this one as the characteristic equation if we are under second order differential equation. So solving for m, to compute for the solution of the equation of this, we will try to compute for the value of m. Since the second term is missing, it's an easy money. M square will be equal to negative 100 after the transposition. M now will be the square root of negative 1 times 10 square, which is 100. Negative 100 is actually negative 1 times 100, right? So we try to segregate the 1 inside. The value minus 1 is actually equal to g square, okay, times 10 square. So what will come out will be a g square times 10 square. They are both perfect squares, so we remove the radical sign. We remove these two here, we remove these two, Okay, so m now will be plus or minus j10. So actually what comes out for the value of m is actually a complex number. And luckily, the real part is actually missing. The real part alpha is equal to 0. This is under case number 3. And beta is actually 10. Actually, the unit of this beta here is radians per second. Okay? So, if we try to recall the formula on how to take the solution under case number 3, it is actually this. A raised to alpha t times the quantity k1 cosine of beta t plus k2 sine of beta t. Okay? Since alpha is 0, 0 times time will be 0, e to the 0 will be 1, so this will just become 1. Right? So 1 times this, it is this. That's our general solution now. It will be, y will be equal to k1 cosine of 10t plus k2 sine of 10t. This is now the equation of the motion of the spring as it moves down and up. Moves down, up, okay, until the time that it will stop, okay? This is general solution, so we must have to bring out the particular solution. At time t equal to 0, y is equal to 0.4t. Meaning, initially, we stretch the weight at a distance of 0.4 feet below the equilibrium position, right? So at y is equal to 0.4 feet, the time is actually 0. So we place it here. At time t equal to 0, we push it down, then we release it, meaning at time t equals to 0, y is actually 0.4 feet, right? So using this condition here, we place back on the general solution, 0.4 will be equal to k1. Okay, let's try to simplify a little bit. At time t equal to 0, 10 times 0 will be 0, and the cosine of 0 is actually 1, so this is times 1. Plus k2, 10 times 0 will be 0, and the sine of 0 is 0, so k2 times 0, this is k2 times 0, so this is now 0. Or actually, the second part is actually gone, right? Because the multiplier is 0. And we can compute for k1 now. k1 is just 0.4 over 1, or k1 is 0.4. So actually, by bringing out this initial condition, we now know the value of k1. Okay? So as a partial general solution, what will come out will be 0.4 cosine of 10t plus k2 sine of 10t. This is now actually the particular solution, but for the meantime, we do not know the value of k2. So we will try to compute for the value of k2 for the solution to be particular. We will try to take the first derivative of this. Okay? This is y with respect to times. This is y. Taking the derivative of both sides, the derivative of y with respect to time is dy dt equal to the right hand side, two functions, right? Cosine function, sine function, constant times the function, so it will be that constant times the derivative of cosine, negative sine of 10t, times the derivative of 10t, which is just 10 times 1. The second part, product also, k2, and the derivative of sine t is actually cosine of 10t times 10. Right? The first one is negative because the derivative of a cosine is negative. So dy dt after the simplification will be 0.4 times 10 is negative 4 sine of 10t plus 10 k2 cosine of 10t. So after taking the first derivative of y with respect to time, apply again the initial condition to compute for k2. At time t equal to 0, dy dt is equal to 0. At time t equal to 0, okay, we release the weight. We didn't push it, right? So actually the initial speed is 0. So at time t equal to 0, dy dt is equal to 0. So this will now be 0. We are following this. Equal to negative 4. 10 times 0 will be 0. Sine of 0 will be 0. So this is negative 4 times 0. So actually the first part is gone. Plus 10k2. At time t equal to 0, 10 times 0 is actually 0. The cosine of 0 is actually 1. So this is 10k2 times 1. Right? So k2 now will be 0 over 10. Or k2 is just 0. Because the left hand side is 0, right? So 0 divided by 10, k2 will be 0. So to bring out the resulting equation now of y as a function of time, meaning the equation of the motion, we will follow this. Substitute the value of k2, but k2 is actually luckily to be 0, so this is actually 0. So what comes out for the equation will be y equal to 0.4 cosine of 10t. That's the equation of the motion. As we stretch the weight 0.4 feet below, then we try to release it. That's the equation of the motion. Actually, it goes up, goes down, goes up, goes down. But whether you like it or not, until a certain time, it will go to the so-called equilibrium position. So actually, the graph is actually this one. And the amplitude is actually this portion here, this one. So the amplitude is 0.4 feet. Initially, because we stretch it 0.4 feet below, right? It will go up 0.4 feet, then later on, it will go down. But it will not reach that 0.4 feet again. It might be a value less than 0.4 feet, maybe 0.3. Then it goes up 0.3. Then it goes down again. But as it goes down, it will not reach the value 0.3, maybe value less than 0.3. It will be 0.2, 0.2, 0.1, 0.1 till it become stationary. So actually, this is the graph. To compute for the so-called frequency, frequency is actually represented by beta 2 pi f under oscillatory motion. So if we know beta, we could compute for the frequency, right? The frequency now will be equal to 10 over 2 pi, okay? Or this is 5 over pi cycles per second. It moves like this, 5 cycles per second. 5 like this per second. It's 5. That's the meaning of this. And how about for the total time? Oh, that's an easy money also. Under oscillatory motion, easy money. If we know the frequency, we could compute for the time. Because time is actually 1 over frequency. So frequency now will be equal to 1 over time. So this should be 1 over, what is time? Or frequency? 5 over pi. Okay? Or frequency now will be pi over pi seconds per cycle. It's the reverse of time. It's less than pi over 5 is less than a second, right? Seconds per cycle. Meaning, 1 cycle, it will not take more than, it will not reach 1 second. It's just only pi over 5 seconds. Around 0.6 maybe. Okay, that's it, guys. That is an application problem that involves oscillatory motion, and the solution is actually by using second order differential equation and by using the formula force equal to ma. Okay, that is one of the equation under what they call this Newton's law. If a body is moving, okay, the equation should be something like force is equal to its mass times acceleration. For the left hand side, it could either be positive or negative. If the force is with the motion, it should be plus. If the force acting on the body is against the motion, it should be negative. That's why the left hand side is negative. Okay, guys? Oh, that's it. I will try to repeat the last portion, the force equal to MA. The force acting on any body that is moving is actually equal to its mass times acceleration, right? If the force acting on the body is goes with the motion, it should be plus F equal to ma. Go with the motion. Go. Okay? If the force acting on the body is against the motion, it should be negative. And this should be equal to its mass times acceleration. This is against. Okay? That's the part of the solution where we formulated the resulting second order differential equation. It came from this equation A. But the significance of the plus and minus, if the force acting on the body is go with the motion, it should be plus. If it's against the motion, it should be minus. Okay, that's it, guys. So for those who are taking differential equation, this is for you guys. Okay, if you like it, please click like. If you want to subscribe to my channel, please click subscribe. You will get something from it. And if you want to share it to your friends, you can share it. Good evening, Los Angeles.